Okay, thank you very much. I'm Jorge Baranda. Thank you for the introduction. And yeah, today I will present this work that has been done a collaboration. Well, it's an ongoing collaboration with SRS and Telefónica. Okay, in this presentation, yeah, today I will present the under the hood of this demo that you will be able to see on Thursday during the demo session. Okay, so in this presentation, as I mentioned, I will enter in some technicalities about the motivation, what has been the methodology to build this demo, the objectives, also the key concepts work during the elaboration of this demo, and then finally I will present the setup under demonstration and some quantitative results. Okay, so yeah, this is I will start with the introduction. So we know that during the last years, the architecture of next generation mobile networks has experienced a big change. And this is due to the application of softwareization, cloud native principle, and open interfaces. This allows the disaggregation of monolithic components into network functions and promotes the interoperability thanks to the open interfaces among multi-vendor providers. But not only on the architecture has been a change. And I think the most of another big component of the change is in the management aspect, where management and orchestration procedures provided also by the SDG projects like open source Mano or TeraFlowSDN controller allows to perform flexible and dynamic deployments and also introduce dynamicity in the management, which allows automated and portable deployments, which is easy if you want to move one thing from another or to replicate your setups. So, okay, given this context, the objective of this demo was to create an almost zero-touch sRAN-based mobile network with over-the-air transmission capabilities and split 7.2 possibilities. Then achieve automation on the deployment of the mobile network entities, spanning from the mobile core to the RAN, and enable a distributed and on-demand deployments, also with slicing capabilities using cloud-native artifacts. As of so, the core and RAN is separated by a transport segment, and we also wanted to automate the configuration of transport network slices for the final goal of create an end-to-end slice mobile network from the core, transport, and RAN. Okay, so yeah, in order to do that, we follow this methodology. Okay, so first we have to verify the capabilities of the open source code for the mobile network entities, like Open5GS for the mobile core and srsRAN for the RAN elements. And we check the configuration capabilities, thinking on having in mind a cloud native environment. So for instance, we need to know which ports were exposed between entities in order to enable them during the deployment. Also, how the different processes, the software processes bind to the interfaces. So in order to announce external addresses to be able to intercommunicate different components, network entities. So based on that, we generate the Docker containers scripts where we also include the custom scripts, because we need to, at the configuration process or when launching the mobile network entities, we will have to rewrite some parameters depending on the cluster where it executes, and in order to enable portability. And also, of course, include some code patches derived from the first step. With that, we created the Helm chart packages, and we included them in open source Mano BNFs and network service packages. So we created the enough parameterization to be able to customize the deployment and the configuration based on our system. and also to provide different configurations in terms of number of slices and MCC, MNC, etc. Then we validate this deployment through Etsy open source Mano, and once validated, we could define the appropriate configuration files for our deployment scenarios. That is, which is changing from one cluster to another. This is on the, let's say, computing part. Then on the transport part, we develop a transport network slice controller to automate the slice instantiation in the transport network. This is consuming 3GPP and IATF slice models, and it interacts with TeraFlowSDN to configure layer 2 VPNs. And yeah, to validate this also, we emulate transport topologies using the IPNG virtualization software. So summarizing, the key concept working in this demo was the CU and DU disaggregation. So with the help of srsRAN, or they work in the separation of the central unit and the distributed unit into different processes, independent processes that could run in different computers. We help for debugging this and helping this to also to customize or to adapt to a possible cloud native environment. Then we also work on the data plane reconfiguration. That is, we were able to disaggregate the mobile network entities into control plane and data plane in order to also to allow multi-slice or a configurable slice environment. And also combine it with the RAN network components, the CU and the DUs. Then we perform transport network optimization by deploying the transport network flows in the slice of the slice mobile network, following the requirements that were requested. And yeah, for the final point of deployment, an end-to-end slice, checking what is needed in RAN, in transport, and core. Okay, so here you have the system architecture that we employed in this demonstration. So this deployment is distributed between Telefonica Research Lab and also CTTC Lab. And on the computing side, we have 4 commercial off-the-shelf servers that are we have the Mano system that is powered by an instance of Etsy OSM, and then 3 different independent servers that are running each one a Kubernetes cluster that represents different points of presence, from the edge through the regional and the central cloud. Then at the radio access network components, we have a commercial Lighton RU for over-the-air experimentation, and a Falcon switch providing the precision time protocol signal to the edge cloud. And then in the transport side, we have the transport network controller server that has running the network slice controller, and also the TeraFlowSDN controller that it's controlling the routers that are in the IPNG emulation. For this emulation, we use a Cisco XRF 9000 routers. So, okay, during this demonstration, we have the following cloud native artifacts. So as I mentioned, for the mobile core, we have Open5GS, and it has been separated control plane, and then SMF and UPF. So depending on the configuration of the control plane, well, we can define the number of slices, and then the components devoted to the slice, the SMF and UPF, can be started on demand. Then we have the RAN part, the disaggregation. We have an artifact for the central unit, another one for the distributed unit featuring open front haul capabilities, and another one to perform the precision time protocol synchronization for for the server hosting the distributed unit. So yeah, based on that, we have this distribution of components in the different servers. So on one hand, at Telefonica, we place the control plane of the mobile core and also the slice components for slice number 1. Then in the regional cloud, we have the components for the slice number 2. And then in the edge cloud, we run the CU/DU as different artifacts together with the precision time protocol. And then the CU connects to the UPFs and to the AMF running in the core control plane through this transport server. Here you have a detail of the graphical user interface of the Mano system. Here, it allows us to connect to an instance of open source Mano that we want, and then based on that, we can select the network service that we want to deploy, the Beam account or the Kubernetes cluster that we want to use, and then provide a configuration file for the server. So from one part to the other, for instance, the different mobile network entities of the core, the AMF or a UPF, SMF, are exchanged through, are presenting an IP address. So, and each cluster has its own set of IP addresses. This graphical user interface allows you also to define multiple network services at a time and then start all of them by interacting with open source Mano. Here you can see, once deployed, you can see where they are placed in the different servers. Here you have the transport network controller OpenAPI definition. Currently, these are the endpoints for the TeraFlowSDN controller, and it has another module for the Ixia controller. And yeah, here you can get and to create new slices and to retrieve which are available, and then also to query to query the requirements of a specific slice and modify the parameters. And whenever you set up a transport network slice, then it is translated into a layer 2 VPN service under TeraFlowSDN for the topology uploaded. Then here we have some results, quantitative results of this demo, just to frame the time it takes to perform these operations. So here you can see a box plot of 50 repetitions of the instantiation of different artifacts. So we have on one hand the control plane, the UPF or CU and DU. And here you can see that this is the time registered by the deployment of open source Mano. It takes around 30 seconds to perform the instantiation on average of 32, sorry, of one artifact. For the control plane, there is more variability because there are multiple pods involved, and depending on the order of starting, they need to perform some restarting to check the dependencies. Okay, then we perform another experiment checking what happened if the different images for the containers are not available in the cluster. So in this case, we repeated the 50 instantiations, but every 5 repetitions, we deleted the container in the cluster. So this is the spikes that we can see. Okay, in this case, the containers are stored in Docker Hub. So if you need to download them from this repository, also depends on our lab connection and the congestion in our network, because it is changing from morning to night. Okay, this is during the morning. But we saw that, the worst case was to download the CU, the srsRAN container. CU and DU are using the same container, as well as Open 5GS control plane and user plane. But nevertheless, this is around 100 milliseconds. So for a single for a mobile network of one G-Node B and so on, you can have it the end-to-end in less than 5 minutes, at least the computing components, okay, the network functions. And here we have the results obtained for the different, for setting the network, the different network slices. In total, we exploit the 3 available paths in the topology I show in the architecture, and on average it took around 15 seconds for deploying these flows. We exploit 3 because we have three flows: one for the control plane from the CU to the AMF, and then 2 for the CU to the different UPFs for implementing the data plane. In other experiments, we saw that if we perform the 3 operations in a row, it was less time, around 30 seconds, rather than 3 times one of these. And this is because of the communications between TeraFlowSDN and the different routers. Because in here you have to open the communication channel every time, but in the other case, you only need to open once. Okay, and with this I finished the presentation. Let me remind you that we will be during Thursday on the demo session, and we have 5 minutes for question and answer. Thank you very much for your attention.